So what we have seen is how the MAC layer works, how the routing layer works. Okay. So now what we will see is how the TCP layer works. What is the impact of wireless and mobility on the TCP traffic. So just to quickly recap what is TCP, this is basic undergraduate stuff. So TCP basically does reliable ordered delivery. Okay. It has a notion of acknowledgements and retransmissions. Okay. It maintains end-to-end semantics. Okay. So the acknowledgements are sent only after the data has reached the receiver, right. It implements congestion avoidance and congestion control. Okay. So the basic mechanism in TCP is you have a TCP sender and you have a TCP receiver, right. It doesn't matter whether these are connected through wired links or wireless links. Okay. It doesn't matter whether it's a single hop link or a multi-hop link. This is the basic behavior of TCP. So you have a TCP sender. So first what will happen? TCP sender will send one packet, assuming that the handshake, three-way handshake has happened and all that. Okay. So the TCP sender will first send a packet. At this point, the TCP sender will set up what is called the retransmission timeout. Okay. It will set a value for the retransmission timeout, saying basically what that means is, if I don't get the ACK before this time, okay, so this is the data and this is the ACK, right. So if I don't get the ACK before this retransmission timer expires, I am going to assume that this packet has got lost and I am going to retransmit the same packet again. Okay. So that is your retransmission timeout which is set. So that is one thing to remember. The other thing to remember is the TCP sender need not send just one by one, but it can send multiple packets in the same round, correct. So I can send 4 packets at one time and get back the acknowledgement for all 4 of them, right. That is also possible. Okay. So now given the question that how many packets should I send at any given point of time. So how do I begin the whole process? Okay. I don't know. See, basic question is the two things that TCP does not know. One is what value, and what's the other thing it doesn't know? How many packets, right. Basically these are the two key questions facing TCP. Because if I get this wrong, what will happen? If I get the RTO value wrong, then either I am going to wait for too long before sending the retransmission. The packet may have actually got lost, but I may just be waiting because I have a very large value of my RTO timer, or I may be doing duplicate transmissions unnecessarily. If I am just going to wait for a short duration, the packet may have got through, the acknowledgement may be on its way, but I may have panicked and send the packet again. So it is very important to get this RTO value correct. And the second question is, so the impact of getting this wrong is retransmission, that controls your retransmission. And the other thing is how many packets to send in each round. How do I know that? What does it control? That decides my throughput, right. That decides, so if I am going to send one packet, wait for the acknowledgement, send another packet, wait for the acknowledgement, then my throughput is going to be lower, correct. So how many packets to send in each round is what determines the throughput of my TCP connection, correct. The throughput of the connection will depend upon how many packets I am able to send in each round. Now what is the problem in this case? The problem is TCP does not know what is the network on which it is operating. It does not know whether the receiver is on a machine which is on the same LAN, or it does not know whether the receiver is on a machine which is halfway across the world, right. So it has to take different actions, but it has to figure both of these things out. Okay. So how does it do that? So which is the easier one? How many packets to send in each round is basically easy, right. So what it does is the TCP sender will send one packet, wait for the ACK, right. If the ACK comes within the RTO, then in the next round I will send 2 packets. If both these ACKs come back within the same round, right, within the same RTO, then in the next round I will send 4 packets, right. So that's the way I am going to grow the network exponentially, right. So what is this phase called? Slow start, right. This is called the slow start phase of TCP. So slow start, unfortunately it's a misnomer, right. It's not starting slow, it's growing exponentially. After 4 it's going to send 8, 16 and so on, right. So is this going to continue forever? If I continue with this, so slow start basically means double the number of packets. So it does a bunch of optimizations. So when I have 4 packets which are sent, instead of sending back 4 individual acknowledgements, TCP can also send what is called a cumulative acknowledgement. It can send one single acknowledgement to acknowledge all the 4 packets that it has received. Okay. So that's called the slow start phase. Now you don't want to go on doubling all the time, right. If you go on doubling all the time, what's going to happen? You are eventually going to congest the network. So after a certain point, it enters into what is called congestion avoidance or linear increase. After a certain amount of time, it's going to go into a linear increase phase instead of doubling. So if you look at it in a graph format, this is how it will look, correct. This is the basic TCP behavior. You have what's called the slow start threshold, which is defined by as a default parameter, okay, as a default startup parameter, the slow start threshold will be defined. So you will keep on sending twice the number of packets up to the slow start threshold, and after that point you are going to send linearly increasing the number of packets, okay. When does this guy stop increasing and become flat? When the ACK stops coming, I have to go down, right. So if any of these ACKs does not come, there are a whole bunch of actions which TCP can take, okay. There are lots of flavors of TCP, TCP Tejo, TCP Reno, TCP SAC, TCP New Reno, okay, TCP Vegas. All of these, each of these will take different actions depending upon what to do when an acknowledgement is lost, okay. So in some cases, if this acknowledgement is lost, the TCP sender is going to drop it all the way down to 2 and start all over again, okay. In other cases, it will just drop up to this point. In some other cases, it will drop only up to half of the current value, okay. So different versions, flavors of TCP take different actions, okay. If everything goes on continuing fine, then what happens? Does this go on increasing? So if this goes on increasing, at some point you will reach the maximum capacity of the receiver's buffer, correct. So at some point the receiver's buffer capacity will be reached, and you are going to stop at that value, correct. How does the sender know what is the receiver's buffer capacity? In the window advertisement comes in the acknowledgement. So in the acknowledgement, so when the receiver is sending an acknowledgement back to the sender, the receiver is just going to put one value into that acknowledgement saying that I have so much space left in my buffer. So based on how much space the receiver has got left in the buffer and what is the current congestion value of the network, the TCP sender can take the action. So we have seen that, so this is what is basically termed as the window based flow control or the sliding window protocol, okay. So the window size is a minimum of the receiver's advertised window, okay. Advertised window means the value which I am putting in the acknowledgement, and the congestion window, which is the value that we have seen for this graph as it grows on, okay. So that is called the sender's window. So sender keeps track of what is the acknowledgements that I have received, it keeps track of what are the packets that are yet to be transmitted, and it knows that so many packets are in the flow, okay. Is that making sense? Okay. So then the key way of TCP detecting packet loss, okay, so in the wired network, remember that TCP was invented for the wired network. So in the wired network, what is more frequent? Packet loss happens more frequently due to congestion in the network and less frequently due to errors in the network, okay, because the errors are very low. Okay. On the other hand, congestion in routers is very high. So it's possible that packets get dropped due to congestion more frequently than due to errors, right? So that is the what does TCP do upon detecting packet loss? It's basically going to do a retransmission. So there are two things. It can okay. So this is one of the actions that it can take. If there is a timeout, what do you mean by timeout? The retransmission timer has expired, but I have not got the acknowledgement back. So in that case I have grown up to this value. So one flavor of TCP will drop the sending window, as it is called, all the way down to 2 and restart again, and the value of this threshold is half the value of the current window. Okay. So initially I started with a slow start threshold of 8. So I doubled quickly up to 8. Then I started increasing linearly. When I was sending 20 packets at a time, I didn't get one of the acknowledgements. When I missed one of the acknowledgements, I just take very conservative action. So TCP in that sense is a very conservative protocol. I take a conservative action of dropping back down to the original value, but instead of climbing exponentially up to 8, I will now climb exponentially up to half this value. Okay. So that is the mechanism of TCP, how it behaves after timeout. Then there is also another thing called fast retransmit. What is the notion of fast retransmit? Fast retransmit happens when the receiver gets packets which are out of sequence. Okay. So suppose you are sending me packets 1, 2, 3, 4. Okay. I got 1, I got 2, then I get 4. Okay. So when I get packets out of sequence, what the receiver will do is it will send duplicate acknowledgements very quickly, okay, to signal to the sender that some intermediate packet has not yet reached, okay, which again means congestion in my network, right? But it's not as bad as the acknowledgement not coming back. Okay. So what TCP does in this case, so this is the other mechanism. What it does in this case is, instead of dropping the sending window all the way, is going to drop the sending window only up to half the value and just directly enter the linear increase phase. Okay. So this is basic TCP behavior. What is throughput here? Throughput is the area under this curve, right? Whatever is the area under this curve, that is your throughput of the system, correct? So what you want to do is, you want to try to maximize the throughput of your network. Okay. So now what happens in TCP is, because the wireless channel has bursty and random errors, okay, TCP gets confused. Okay. So every time there is a packet loss, TCP assumes that the packet loss has happened because of congestion in the network. Okay. So that becomes a fundamental problem from the viewpoint of TCP. Okay. So what happens here is, burst errors can cause timeout, right? What is a burst error? Many bits in error contiguously. Okay, when many bits are in error contiguously, that's a burst error. Burst error can affect more than one packet at a time, so it can cause timeout. Random errors can cause one packet to get lost, or one packet to not be assembled properly, so that packet's acknowledgement will not come. Okay. So random errors can cause fast retransmit, burst errors can cause timeout. Okay. The key problem is TCP cannot distinguish between packet losses due to congestion and transmission errors. Okay. So what happens is, it unnecessarily reduces the congestion window, and so your throughput is going to suffer. So I have, let's say, a fixed host, I have a wired network, and I have a receiver. In this case, TCP works fine, correct? Fine as in fine within the limits. So now I am going to take it to a scenario of having fixed host, I have a wired network, I have a relay or a base station, and then I have a wireless network, and I have a mobile host. So this is the scenario which I am now considering. From just simple wired, I have gone off to wireless. And what is the third scenario? Third scenario is I have multi-hop wireless. Okay, so I say the third case could be that I have host 1 wireless, some other host K wireless, host N. Okay, so we have to try to understand how TCP behaves in these three cases, right? So in the first case, we have standard TCP behavior. Whichever one is being implemented, that standard TCP behavior is used when both the nodes are in the wired network, right? So let's look at case 2 now. So let's try to come up with some solutions and then see what is the effect of these solutions. Okay, so this is our scenario. What do we know? We know that in such a scenario where I have a fixed host, a base station and a mobile node, on this wireless part of the link there could be burst errors or random errors, as a result of which TCP is going to panic. The TCP sender, so let's say this is my TCP sender and this is my TCP receiver. So this guy is going to panic if there is any packet loss here, and the sender is going to drastically drop the throughput, which again is going to lead to bad things because my wireless network already has very low throughput. Okay? Okay, so how do I fix this problem? So that is what we are trying to figure out. How does TCP infer that? See, as far as the sender is concerned, okay, this fixed host sender is concerned, it does not know that is across a wireless link. Okay, the TCP sender cannot be notified that there is a wireless hop in this end-to-end connection, right? If it knew that, then it can obviously take some other action. So it has to somehow figure that out. So maybe that happens for some other network, some other node which is in the wired network itself. So it should not do that for the node which is in the wired network, right? So let's look at one by one the suggestions. Explicit packet drop notification. What do we mean by this explicit packet drop notification? So the router, so there is a ECN flag, right? Explicit congestion notification flag is there. So we can use the ECN flag and the router sends that to the TCP sender. Okay. So now the question is, how does the router know why the packet got dropped? If the router is dropping the packet, then it's okay, right? Do I know as TCP receiver, does the TCP receiver know, right? The question is, does the TCP receiver know the cause of the packet drop, right? So if the receiver could know that this is due to wired congestion or due to wireless error or due to wireless congestion or due to wired error, if it could classify the packet drop into one of these four categories, okay, then I can send an explicit notification to the sender and I can tell the sender that, okay, see, this packet got dropped for such and such reason, and the sender can take appropriate action. Correct? How easy or hard is this? Think of it like this. What is the information that the TCP sender have? TCP sender just knows that, okay, I am receiving packets. It can just know that I missed receiving one of the packets. How do I know why I missed receiving one of the packets? So receiver can notify to the sender by simply using the acknowledgements. That is easy. How does the receiver know why it didn't receive a packet? I can't make that out. Okay, so there are lots of schemes which try to study things like inter-packet arrival time. Okay, so if I am receiving packets on a continuous basis, one every, let's say, a few milliseconds or so, and then suddenly I lose a packet, then I will kind of guess that this may be because of an error. Okay, but all of these are guessing techniques. Okay, so there is no clear way of determining that I have lost a packet and explicitly notify to the sender the reason for the loss. Right? So what do we do? Now that this is split into two parts, can I just divide the connection into two parts? I have one TCP connection here, I have another TCP connection here. Okay, So I handle the wired part and the wireless part separately. Okay, so that was the first suggestion that was tried. Okay, and that is called your split connection approach. Okay, so this was one of the earliest strategies that was tried. The end-to-end TCP connection is broken into one connection on the wired part of the route and one connection over the wireless part of the route. Okay, so let's try to answer the other questions. Where all do I need changes in order to implement this? Do I need to make changes here at the fixed host? No? No. I need to make changes at the base station, right? Who controls the base station? The operator. Okay, so I need the operator's help in order to implement this. That is one thing. What else happens in such a system? Suppose the fixed host has sent a bunch of packets to the base station, and then the base station goes down momentarily before it has been able to forward the packets to the mobile host. Okay, what will happen? As far as the fixed host is concerned, the packets have reached the mobile host, right? See, that is the key reason why we have TCP, is that we have kind of blind faith in the guaranteed delivery semantics, right? TCP basically knows, TCP sender knows that if I have got an acknowledgement, then the packet has reached the receiver, right? So that kind of faith exists in the TCP. Now what we are doing is, the TCP sender has got an acknowledgement, right? See, TCP sender gets an acknowledgement from the base station, but the packet really has not reached the mobile host. Now if the base station goes down, the sender would have removed the packet from its sending window, saying that this is already acknowledged. Okay, so that is the key problem with the split connection approach. Okay, so what happens here is, the packet comes from the application layer, goes up to the TCP layer. This is one separate TCP connection, and then from here there is a separate TCP connection which goes to the mobile host. Okay. So one problem is, I have to maintain per connection TCP state. Right? What does that mean? For each connection that is made, suppose from the mobile host you are connecting to, let's say, Google 3 times. Okay, so you will have to maintain state for 3 different connections here at the base station. If there are 100 such users who are doing that, you have 300 connections which the base station has to manage, right? And it has to be able to do the splitting, it has to be able to send the request on this direction. See, as far as the sender is concerned, the base station is the client, right? The base station is the receiver. So the sender doesn't care, he's just going to send the packets off fast. Okay, so that is the key problem with the what is called the split connection approach. One of the earliest such mechanisms was called ITCP, okay, indirect TCP. So there are many variants of TCP. There is ITCP, MTCP, STCP, all kinds of variants are there. Okay, but we can just try to classify them into what is the approach that is taken. Okay, so this was one strategy we looked at. The second strategy is a split connection. The split connection, the problem with split connection is end-to-end semantics are not retained, are broken. Let me just write broke. Okay, end-to-end semantics are broken, and per connection TCP state. Okay, what happens if there is mobility in such a scheme? If I am maintaining per connection state, I move from one base station to another base station, what happens? Yeah, so when I am moving from one base station to another, the entire state has to be moved from one base station to the other. Is that making sense? Otherwise, it's as though all those packets got lost, right? So mobility, again, entire state has to be moved from one BS to another. So this is what is called hard state. If you don't move that state, then again bad things are going to happen. That is the meaning of hard state. Okay, soft state means if you don't move that state, you are just going to lose some efficiency, but bad things are not going to happen. Hard state means if you don't move it or if you don't take that action, then bad things are going to happen. What is the bad thing that happens? As far as the TCP sender is concerned, it doesn't matter whether the base station has gone down or whether the mobile host has moved. No? It has received the acknowledgement, so it's going to assume that the packets have been delivered. Correct? So that is the key problem. So how do we fix this? right? So the fix for this is, in order to maintain the end-to-end semantics, BS withholds ACK to fixed host until it receives ACK from mobile host, right? Suppose I do that, okay? I withhold the acknowledgement to the fixed host until I receive an acknowledgement from the mobile host. So what will happen in this case? Some other problem gets created, right? So the moment I say I am going to withhold the acknowledgement, now you don't know how long the wireless link retransmission is taking, right? Suppose the wireless link retransmission takes beyond a certain amount of time, so this can cause the fixed host to retransmit. So all the RTO calculations, all of those things can go wrong. So what do we do? Right? So there are 2-3 schemes. I'll just quickly tell you about one of them. So the other scheme is called snoop protocol. Okay, you snoop on the packets that are going. So the base station is going to snoop on the packets. So it's going to buffer the data packets at the base station to allow the link layer retransmission. Okay. And when duplicate acknowledgements are received by the BS from the MH, okay, it will retransmit on the wireless link. Okay. So this will try to prevent the fast retransmit at the TCP sender. Okay. So what you are saying is, I am not going to do a split connection at all. I am going to allow a single TCP connection from the fixed host to the mobile host, except that in between I am buffering. Okay. So when I am buffering packets in between, this guy is continuously sending me acknowledgements. I am going to monitor the acknowledgements that are coming. If he says I have received packet 1, I have received packet 3, then I know that he did not receive packet 2. So I will just pick out packet 2 from my buffer and send it back to him locally, instead of sending that acknowledgement all the way back to the fixed host. Okay. So this is one protocol. Again, it has a problem. Okay, what is the problem? If there are many packets in the, see, this buffer is a very passive buffer. The buffer in the base station is a very passive buffer, right? I'm just going to, packets are going past, I'm just copying one and keeping it with me. It has nothing to do with the fixed host. Fixed host doesn't even know that the base station is copying these packets. Okay, is that making sense? The fixed host, as far as the fixed host is concerned, I am only communicating with the mobile host there at the other end. Okay. The base station in between is just copying some of the packets. If the mobile host is giving me an information that some of the packets are not getting through, I am just going to do a local retransmission. That is the only scheme here. Okay, suppose the mobile node is down, then yeah, how many times it should retransmit, that's the question, right? Let's say the mobile node is up, there is still a problem. The basic problem is, now in this case, snoop, the word snoop should give you the hint, right? I have to look into the packet. Okay. See, I am looking into the packet to find out which acknowledgement does this correspond to. Okay. So now look at it like this, TCP packets are handed over to IP packets, right? It goes into an IP packet, then it goes into a MAC packet, right? Then it is sent on the wireless link. At the base station again it comes up to the IP level, correct? Now suppose I am doing encryption at the IP layer, right? Then no amount of snooping is going to help. If I have encrypted the packets at the IP level, right? So if I am using SSH or one of those mechanisms, then I cannot snoop into the packet to find out which packet is this, which is the acknowledgement to which it corresponds to. Okay, so the key reason why snoop fails is in the case of encrypted packets, and all these other reasons are also correct, but the main thing is what to do in case of encrypted packets. Okay, the other thing is what happens when we do handoff. Okay, so handoff, we have already seen that in the split connection approach, hard state must be moved to the base station, new base station. Okay. So in the Snoop protocol, it turns out that it is soft state. Why? Because we still have a end-to-end connection. The TCP sender and the TCP receiver are end-to-end, right? So that is why the state is soft state. The base station is just copying some of the packets, right? So while the new base station builds new state, packet losses may not be recovered, but that's okay. So frequent handoffs are always a problem for schemes that rely on significant amount of state. Okay. So how do I handle handoff? Last question on TCP. How does the TCP receiver prevent TCP sender from reducing window during a handoff? That is the question. So basically what I have is a fixed host. I have a base station 1. I had a mobile host which was connected through it, and now I have a base station 2, and this mobile host has now connected to the new base station. Okay. So the mobile host has moved from one base station to the other. Okay. So now my problem is that it's going to take me some time to move from this base station to the other one, correct? So if I take too long, this guy is going to be looking at his RTO timer. The moment that RTO timer expires, he is going to take a whole bunch of drastic actions, right? How do I prevent that from happening? So you have to fool the TCP sender in some way to prevent it from taking that action. How do I fool it? So the key thing here is what the receiver does in this case is, it advertises. How do you stop the sender from sending you packets without dropping the window? You have to advertise a window size of 0. See, even in a wired network, when the receiver is out of buffer space, okay, what will it do? In the acknowledgement it will say 0, I am out of buffer space. What will the sender do at that point? It's not going to transmit packets, or it's not going to set up any timers and all that. It's just going to wait, right? So the same thing it can do at this point. It can advertise a receive window of 0 on the acknowledgement itself, right? So the window advertisement goes on the acknowledgement. So I can advertise a receiver window size of 0 on the acknowledgement, and so the sender will go into what is termed as the persist mode, right? So advertise receiver window of 0 and puts the TCP sender into persist mode. So I'll just send a 1 byte packet to see what the acknowledgement is. If the acknowledgement says that okay, now I have buffer space, then I can start sending packets again, right? If the acknowledgement continues to say that I have no buffer space, I have not finished processing what you have sent, I will wait for some more time. Okay, so that is called the persist timer. So there are 3-4 timers associated with TCP. One is the retransmit timer, the other is the persist timer. So whenever the persist timer expires, I will send a 1 byte packet. I will see what the acknowledgement I get. Depending upon the acknowledgement, I can now decide to either open up the window or go back into persist state. Okay, so that's basically what TCP will do. Okay, so now answer this question. If it is fine, now answer this question that this mobile host doesn't know that it's going to get disconnected, right? If I knew that I'm going to get disconnected in the next second, then I can send this 0 window advertisement. So there are multiple proposals here. So because the mobile host does not know, it cannot anticipate. See, there is one scheme where I will try to anticipate that maybe I'm going to get disconnected, so let me play it safe and send a 0 window advertisement. Okay. Otherwise, the mobile host will always come to know about the disconnection only after the disconnection has happened. If at that point you say, okay, let me send a 0 window advertisement, anyway it's not going to get across, right? So chaos has anyway occurred in the system, right? So in that case, what happens is, base station will withhold ACK for 1 byte, okay, and uses it for 0 window advertisement, as it is called, ZWA. So what it does is, so the mobile host is sending acknowledgements to the fixed host. So the base station will withhold the acknowledgement for the last byte. Remember that TCP is a byte based protocol, it's not a packet based protocol. If I have sent you 1000 bytes, it's possible for you to acknowledge receipt of 999 bytes and not 1000 bytes, right? It's not a packet based protocol. So what the base station can do is it can withhold the acknowledgement for the last byte. Base station will know whether the mobile node has got disconnected or not. Once it knows that the mobile node has got disconnected, it can send the 0 window advertisement. When the mobile node connects from the other side, it will now send a duplicate acknowledgement, and the transmission can start. Okay, it sounds very simple. Lots of issues are there which we don't have real time to go through. So when a new acknowledgement is received with the receiver's advertised window equal to 0, the sender enters the what is called the persist mode. Okay, sender does not send any data. When a positive window advertisement is received, the sender exits the persist mode. Okay, so the key point is, on exiting the persist mode, RTO and the congestion window are the same as before. So this scheme, so there are two schemes which are very popular. One is called MTCP, another is called freeze TCP. Okay. So in MTCP, the base station is going to be told the ACK for the last byte. So the problem with MTCP is, now you need help from the base station. Okay, the base station has to do some work for you. Okay. Freeze TCP is the other scheme where the receiver itself is supposed to send the 0 window advertisement. So freeze TCP is kind of a predictive mechanism, right? It will keep monitoring the signal strength, etc., and when the signal strength starts falling below a certain threshold, it will send a 0 window advertisement. Okay, so TCP is also another very rich area for doing projects in. There are lots of such issues. There are lots of such. There are about at least I would guess close to 100 such proposals already in existence on TCP. Various tweaks to TCP to make it work for different scenarios, but still there is no very clear solution which will work well for wireless networks. Alright, so let's try to summarize. So TCP over wireless, basically TCP assumes that packet loss implies congestion. Now that is not valid in wireless environments, right? So the invoking of the congestion control response is inappropriate. Several proposals to adapt TCP to wireless environments. So you can always find cases where your proposal will work well, right? So that's how people write a lot of these papers. They'll do experiments to show that, okay, under these cases the proposal works well. There'll be and then a whole bunch of other people will do experiments to show that under these cases that proposal doesn't work well, so we'll come up with a new proposal. So this happens all the time. Okay, so the question is, what happens now in a multi-hop scenario when there are two wireless hops? So we are coming to that when we talk about ad hoc networks. Okay, so in a multi-hop scenario, see, already if there is a single wireless hop itself, TCP goes kind of crazy. Okay, so in a multi-hop wireless scenario, nobody really knows how to set up TCP properly. Okay, so quite often this problem is compounded because of your 802.11 MAC which is being used. Okay, so 802.11, remember that string topology thing that we did? Okay, we did that exercise of RTS, CTS, people interfering with each other and so on. Now imagine that TCP data has to go in one direction, TCP acknowledgements have to go in the other direction. Okay, so the same node has to pass data in one direction as the data, pass the acknowledgement in the other direction. So it becomes totally chaotic as far as the TCP traffic is concerned. So because you are not able to get access to the medium access medium, right? Because you are not able to access the medium in order to transmit, TCP can time out. Okay, so it becomes too complex for most TCP proposals to be useful in such scenarios. So anything that goes beyond 2 hops of wireless, people just say, looks like I don't need TCP for this, maybe I can do with UDP. Okay. So most of the applications, people tweak with the application. Nobody wants to do FTP over a multi-hop wireless link. Okay. Everybody will talk about a voice over IP or a video kind of an application. No, very safe applications because they don't use TCP. Right. People say, why do I need FTP over a multi-hop wireless link? Or they will make it a fixed link. So those kind of strategies are used. Okay, let's look at ad hoc networks, and we can, if the question is still unanswered, we'll do that now. Okay. So multi-hop wireless basically means that a packet may have to traverse multiple links to reach the destination. So mobility causes route changes. Basically that's what happens, right? If this guy moves off from there, if this guy moves off from here, then my route is going to break. Okay. So there are several questions that I need to answer. So suppose I have, this is my original host movement. Okay. So A is talking to B and these guys move off like this and it becomes like this. So I have to route the data through the intermediate nodes. So there are several questions that I need to answer. First of all, how do I find out where is B? Right? That is the first question that I have to answer. how do I know where is B? So the only solution here is to broadcast the packet. So I am not going to read out the applications of mobile ad hoc networks. Okay, there is a whole bunch of them. 802.11 is the MAC which is used. Okay, let's look at routing protocols. Let's go to one example. Okay, so the key example here is that is a protocol. The first one that was invented in this area was called dynamic source routing, or DSR. Okay, so it works in a very simple manner. I have a figure here somewhere. Okay, so let's say this is the network. Okay, S wants to send a packet to D. Okay, so initially S does not know where is D. Okay, so what will you do? You will flood the network. So broadcast, when you broadcast to everybody and ask them also to broadcast to everybody else, that's called flooding, right? So it starts from one point, it keeps spreading, so that's called flooding. So you start flooding on the network. So S will send a packet to E, C, B, etc., etc. What will go in the packet? Source and the destination to which you are trying to reach. Okay, so that is the broadcast transmission that happens. S is broadcasting with the source ID, and it's saying that I am trying to reach D, and it goes to all these guys. Okay, then what happens? These other guys, they also further broadcast the packet, right? So that is the next thing that happens. They also further broadcast the packet while adding their names to the list. Okay, why is this required? So that I know what is the path, so that I can reconstruct the path. So I am just going to continue this broadcast by adding my own identifier to it, and then at some point it's going to, so all these guys are doing broadcasting, right? At some point the packet is going to reach D. Okay, so D knows that I have received a packet saying S, E, F, J, D. Okay, and D also knows that I have received a packet saying S, C, G, K, D. So D picks one of them to reply. How does it reply? It reverses the route, correct? It basically says that, okay, I got a request through S, E, F, J. So if I go via J, F, E, I should reach S. Okay, so it just reverses the route there, and it sends back a route reply saying that this is the way in which you can reach me, and then the data can flow along the same path. Okay, so that's what is happening. Okay, D does not forward the route request because D is the intended target, and then D sends back a route reply saying that this is S, E, F, J, and D, and then S can send the data along that route. Is that clear? It's a very simple protocol. It was one of the earliest protocols which was invented for ad hoc networks, and surprisingly it continues to be an efficient protocol even today in the face of lot of other inefficiencies, other problems. Okay, so can we say what are the problems in this protocol? So DSR, the basic summary is S sends a route request, okay, what is called a route request packet. Okay, all the nodes append their IDs and forward the route request. D receives the route request and sends a route reply by reversing the route, okay, by reversing the order of the IDs. That's how I know that. Then S starts the data transfer. So what are the problems that we saw? Any node moves, it doesn't have to be just D, right? If any node moves, what happens? Right, mobility can cause route breakage. That is the key problem in your ad hoc networks. Any mobility can lead to route breakage in this. Yeah, you have to go back. So whichever node discovers the route breakage, how do I discover that there is a route breakage? Let's look at this figure, right? How do I discover that there was a route breakage? So let's say F moved away. Okay. So how does E know that F has moved away? Correct. So that is why acknowledgement is very important at the MAC level, right? So E has sent data to F at the MAC layer. Remember, this is not the TCP layer. This is not the network layer. Even at the MAC layer, there is an acknowledgement. Okay, we are using 802.11. So E has sent RTS, it has got CTS, it has sent the data to F, and then it has to get the acknowledgement back, right? So at some point, if F moves away, E is not going to get the ACK, right? So as a result of that, E will know that F seems to have moved away or something has happened. So E sends back something called a route error message to S. So E sends a route error to S, and now S can restart the whole process of trying to find another route. So that is the key, one of the key issues. Okay, mobility causes route breakage. So what people did was they kept on trying to optimize on this thing. So now they said that since E is trying to find a route through some other way, maybe I can cache these routes. Okay. So one optimization that was tried is route caching. Okay. So what do we mean by route caching? See this node H, for example. Okay. H has forwarded the message saying S wants to reach D. Correct? H has no interest in either S or in D. But still it has forwarded the message. What has it gained out of that? It doesn't know where S is. But it knows that if I want to reach S, I can go via HBS, because that is the way the packet has come to me. Right? So whoever is forwarding nodes to me, right? Whoever is forwarding the packet to me, I know what is the path. So I have partial information about the network. Okay. So that's what the DSR guys initially tried to sell it as, saying that we can have this route caching. Okay. Then a whole bunch of people discovered that there is a lot of problems with route caching. Okay. So I may have cached this information. So H may have cached the information saying that this is the route to S. Right. In order to reach S, I will go through B. But the cached information may be old. By the time B may have moved out. Okay. So in which case what you are trying to do is you have to now send the packet, wait for a route error, and only then you are going to restart the whole transmission. Okay. So there are a whole bunch of protocols in this manner. DSR is one of them. Another popular protocol is called AODV, okay, which tries to fix some of these issues with DSR. Okay. AODV. Okay. That tries to fix some of these problems. Then there are a whole other category of protocols which try to which try to maintain a balance between proactively trying to maintain routes versus reactively trying to find the routes. Okay. So we won't go into all of them. What I will do is I will just ask a question. Okay. So is DSR clear to everyone? Okay. Path, is it the shortest path that it will choose, or will it choose any path? Okay. So now here is a very important point in wireless. Okay. So in wireless, the shortest path need not be the one which has the least number of hops. Okay. In fact, that it's not known at all how to determine what is the shortest path. Okay. What is the shortest path? I mean, if you think of it in English terms, the path along which it takes me the least time to travel. That is my shortest path, right? But it turns out in wireless, if you typically in the wired network, that is going to correspond to the least number of hops, correct? But in wireless, what may happen is the path which has the least number of hops may be the most congested, maybe the one on which I have to wait for longest, right? So it may happen that a longer path may actually reach faster than the shorter path. Okay, so it's a messy thing. So again, there are schemes which say, suppose all these networks are also battery powered, right? So there are schemes which say that if I am going to use the same path again, then I am draining the battery of those devices. Okay, so sometimes I will use this path, sometimes I will use other paths, so that the lifetime of my network is increased. Okay, so if you look at the area of sensor networks, this is a very important concept there. How to increase the lifetime of the sensor network. So you have thrown sensors on a battlefield, let's say, or on a no man's land or something, and which are running this protocol in order to route the sensed information. Now if you are going to use the same path all the time, then some of the intermediate sensors are going to die, and so you are not going to be able to maintain the network. So there are protocols which say that I will do a probabilistic path selection. So a lot of work has happened in this area. We are just looking at the most basic thing. Okay, how is security implemented in these systems? There is no security as of now. Okay, so I mean there are a lot of things that could happen, that it's easy to break the system right now, right? Because I could just send a fake route reply security by and large is not so much of data security but of denial of service security, right? If I just send fake root replies, or I could just flood the system with fake root requests, right? I can bring down the system very fast. So there are some proposals to deal with security, but none of them is really well established. See, 802.11 became popular, okay, and when people were talking about ad hoc networks, it turned out that 802.11 was a convenient MAC to assume. Subsequently, it also turned out that 802.11 is creating a lot of problems. But there were already deployments by that time. So nobody now has the time to go and say that let's do a totally different MAC in an ad hoc network, right? So ad hoc networks means you by default you assume that 802.11 is the MAC. See, if there is a base station somewhere, then you can give the job of coordinating the MAC to that base station, correct? But ad hoc by definition is saying that no, all of you guys have come, you have brought your laptops, and then you want to start sending messages from one corner to the other while you are moving around, right? So that is the whole thing. Now there is no infrastructure here, so the only MAC that you can use is sense the medium, see if the medium is free, and transmit. So my question is, what happens? Okay, this is an example of an asymmetric link. Okay, A has a larger transmission range than B. So A is able to reach B, but B is not able to reach A. So now DSR depends upon this fact that I am going to reverse the route, right? I got the route request along one path, correct? So I got the route request along this path. I have reversed the route in order to send back the reply. Okay. Now if these are asymmetric links, then what happens? My route reversal can fail, right? So how do I fix it? What new route? So route reversal fails. So the fix is to do a route discovery from D to S. Okay, I'll do a route discovery. I'll do a new route discovery as though D wants to find a route to S. I'll do a new route discovery from D to S, and flooding is happening. And I will piggyback my route reply on the discovery. Piggyback route reply along with it, right? Is it clear? S has sent a first route request, but since the path is asymmetric, D cannot reverse the route to send back the route reply. Okay, so but it knows the answer, right? It knows that for reaching from S to D, you go by S, A, B, C, D, correct? It knows the answer, but it has no way of conveying the answer back to S by simply route reversal. So what it does is it starts its own route discovery. Maybe it will find some other path, okay, but along that path it will just piggyback this answer. It will just say that if you want to reach me, you come via A, B, C, D, and that's the way asymmetric links can be handled. Okay, so what is the key thing that I am trying to say here? Okay, the key thing I am trying to say here is that if we don't keep into account what is the application, right? Now there are 100 proposals for various levels. If we don't keep in mind what is the application, okay, so if it is an application, let's say like a disaster recovery scenario, okay, you design your solution for that, and then you take the solution and try to put it into another scenario, 99% of the time it's going to fail. Okay, so you have to start from the application. You have to say, okay, this is a military scenario, I have a group of vehicles going in this direction, so that means you have mobility, at the same time the relative mobility is very low. Okay, so you might design a routing algorithm for that, you might design a TCP strategy for that. If you just take that and put it into another scenario, like people going to office and then going back home, so at all times in an ad hoc network, you need to be able to always map all the way from the application down to the MAC. Okay, the whole, your chain has to be complete. If at any one point your assumptions are not matching, then the solution is going to fail. Okay. Okay. So how about TCP in these networks? There are several factors that affect TCP. Wireless transmission errors. Okay. There's one interesting thing that happens with TCP in ad hoc networks. Okay, one is multi-hop routes. Longer connections are at a disadvantage compared to shorter connections. Okay. Can we think of any scenario in which mobility actually helps? See, suppose I am trying to send a packet to him. Okay, so there is n number of hops in between, wireless hops. alright. So the TCP connection is going to be not doing very well, okay. But if because of mobility I happen to go near him, okay, then my throughput can increase, okay. So again such scenarios have to be investigated. So sometimes that is what those are the kind of graphs which one sees, because when you are doing a random simulation you can't make out what exactly is happening in the network, okay. So sometimes mobility also helps because the source manages to come close to the destination, okay. So in those cases mobility becomes a useful thing. More often than not mobility causes route breakage, okay. So it's very difficult to make a categorical statement saying that if I do this strategy then it will always work, okay. So ad hoc networks, if you want to summarize, routing is the most studied problem. Interplay of layers is being researched. This is what I meant by saying, you have to start from the application, keep working down, make sure that all the assumptions are consistent, okay. It's a fertile area for imaginative applications. How many maximum nodes can be there in an ad hoc network? It depends upon the application. Now, as far as deployments are concerned, people have done for tens of nodes, okay. People have not done deployments for hundreds of nodes, okay. So the last topic of this session is wireless metropolitan area networks, okay, 802.16. Now this is again getting very hot. So I debated a while about whether to introduce it or not, but then I thought let me at least introduce you to the topic, because it's a very vast topic in itself, okay. I can go on for half a day just talking about .16. So what is the idea? The key idea, so now this is a mix of ideas that we already have seen, okay. So we have seen GSM. So the reason why we saw two of these technologies in great detail, which are the two? GSM and Wi-Fi. These two we have seen in great detail because those concepts keep recurring, okay. So this is a mix of various ideas that we have already encountered, okay. So the idea is that instead of having wires going from various buildings, various locations, okay, I will have wireless links, okay. So I basically create wireless links from a base station to the various customers, try to achieve something like a cellular performance using something like a Wi-Fi link, okay. So that is the basic approach. So the commercial name for 802.16 is WiMAX, okay, or wireless MAN, okay. So you may encounter these terms interchangeably in the literature, okay. WiMAX is basically a subset of 802.16, okay. So the goal is to provide high speed internet access without wires, okay, and to support applications with different QoS requirements, okay. So the products are not yet out. I mean the initial field trials for WiMAX equipment is still going on, okay. So I think there are a few deployments that are done, but there is no large scale deployment of WiMAX yet, okay. So let's look at this. What is our goal? Our goal is to support applications with different QoS requirements, okay. Now we want to design a MAC. How do we design the MAC? What kind of a MAC shall we use? If I let you speak for 5 minutes and I let that person speak for only 1 minute, I have supported different QoS requirements, right. So a central node, now given that this is a base station and a subscriber station model, okay, a central node which captures both of these is the one which is most useful, okay. So what .16 does is it allows two different types of duplexing schemes, okay. Either you do frequency division duplex or you do time division duplex. What this means is the following. So 802.16 you have a base station. So base station has, let us say, time. I have a time frame. I have subscriber station 1, 2, I have n subscriber stations. So what the base station does is, first it does what is called time division duplex. Basically means, so suppose I have 10 milliseconds of time, 10 millisecond frame. What it says is that, let us say 6 milliseconds is downlink and 4 milliseconds is uplink. First thing it does is it splits the time into two parts, okay. Out of 10 milliseconds, For 6 milliseconds I am just going to be transmitting in the downlink direction, and for 4 milliseconds I am going to allow people to transmit in the uplink direction. Okay, why is the 6 and 4? There is no reason really. Okay, so it's just, you just guess that it could be because mostly people are downloading rather than uploading. Okay, so the uplink you expect mostly requests, on the downlink you expect mostly to be serving web pages and so on. Okay, so generally when you do a TDD system, people try to do a 2/3 is to a 1/3 kind of a ratio. On the downlink I send data to the various subscribers, okay, and on the uplink the subscribers are able to send me data. Okay, so that is basically what is happening. So suppose there is a voice call that arrives at the SS. So the SS informs the BS saying that okay, there is a voice call that has arrived. Now please allocate a connection identifier for this voice call. Okay. So once the BS has allocated a connection identifier, it's just like a token. So after that you don't have to put all these various headers, you are just going to refer to the call by that one number that is assigned to it. So what is the key question here again? Okay. How do I do the uplink allocation? Because that is what is going to determine my quality of service, everything. So in the case of .11e we saw that there were 4 access categories, right? What were those 4 access categories? Voice, video, FTP, HTTP. These are the examples, right? So in the case of 802.11e, this was called access category 1, access category 2, access category 3 and access category 4, right? In the case of 802.16, this is called UGS, okay? UGS stands for unsolicited grant service. What this means is once a voice flow is set up, once a voice connection is set up, right, the base station knows that every 20 milliseconds I am going to have a voice packet going in both directions, right. So without the subscriber station explicitly asking for bandwidth, the base station will allocate because I know the type of flow. So that is why it's called an unsolicited grant. Without you asking me, I will give you bandwidth because I know that the type of flow is a voice flow which has a certain periodicity. Okay, so that's why it is called a UGS flow. What about video? Video is called RTPS. RTPS stands for real time polling service. So how do I do allocations for this? Periodically I am going to poll the station and ask how much bandwidth it is requiring, okay, and I am going to have a certain space allocated in my uplink in order to send the polling request, right. See, even for you to send me a response, I have to give you bandwidth, right. It's not an automatic request reply scheme because on the downlink I can poll you, but on the uplink is when you have to send me the response, okay. So that's why it's called real time polling service. FTP would be called non real time polling service, okay, NRTPS. Because it doesn't matter. See, what is the difference between real time polling service and non real time polling service? In the real time case, I need the service within a certain deadline, right. I need the service, so I need you to do the allocation in the next frame or in the frame after that. Whereas in the FTP case, it's a non real time polling service. I can wait for a while. As long as I get the amount of bandwidth that I am requesting, I can wait for some time. So that is the difference. What is HTTP called? Best effort, okay. So frequency division duplex means I will use one set of frequencies for downlink, one set of frequencies for uplink. Time division duplex is what we just saw, okay. It supports both full duplex and half duplex stations. It also has a notion of adaptive profiles which we won't go into, okay. So this is the example of time division duplex, okay. There is a downlink subframe and there is an uplink subframe. This boundary between downlink and uplink also can be moved, okay. And the MAC is connection oriented. Channel access is decided by the base station. Okay, so there was one question which I forgot to ask. Okay, once I have come up with a schedule. Okay, once I have decided that on the uplink you will transmit for 3 slots, you will transmit for 2 slots, you will transmit for 5 slots, right? How do I convey that information to you? So every downlink I start with sending a beacon, right? What do I put in the beacon? Just like in GSM, no, you have your broadcast control channel, right? So or even in any other system, you will send a beacon. So in the beacon you will say, okay, this is my BSID, and I will also give you the allocation. So everybody has to read the beacon. In the beacon I will say that, okay, you go first, you go second, you go third, you speak for so much time, you speak for so much time, you speak for so much time. Okay, done. So that beacon or that allocation is called a map. Yeah, 1 minute, I will just come to it. Okay, so that allocation is called a map. So this is called a UL map. UL map stands for uplink map. DL map stands for downlink map. Okay, so the UL map and DL map are both transmitted in the beginning of each downlink frame. Okay, so now the question is, what about allocation requests? What do I do with the request? So the UL map simply says that I am giving you 2 minutes to talk to me, right? It does not say that you can say only this or only that in those 2 minutes. So moment there is an allocation in the UL map, you can send a request, or you could send a data. Does that make sense? If a new node arrives in that area, then what will happen? Then the new node has to be configured to understand the base station, okay, and it has to send its first packet in the best effort part. See, connection establishment is always in a best effort mode. Okay, so there will be some part which is left for best effort traffic. Okay, so see, this is how it happens. So first you have the initial maintenance opportunities, don't worry about that. So then you have request contention opportunities, okay, in which new stations could send their requests. Okay, then you have the scheduled data for each different SS. So now how much time I give to each of the SS is totally defined by the scheduler that is being used at the base station. Okay, so scheduling in WiMAX is a good area for you to look at as, you know, potential master's problems or PhD problems, in case you want to look at that. Okay, or I routinely give these problems to students as master's problems. Okay, so just to quickly recap, so in the preamble there is a beacon which has a DL map and a UL map. Okay, the DL map defines what is going to go on the downlink. Why is a DL map required? Everybody is listening to it anyway. So downlink is anyway broadcast, right? Why do I still have a DL map? Suppose I were to say that I am going to teach topics X, Y and Z, okay, and you already knew topic Y, then you can sleep during that time, right? It's the same thing. So if I announce that this is the DL map, I have data for X, Y and Z, then some ABC for whom I don't have data can sleep during that time. Okay, so the DL map is used for power save. So I save power by announcing in the who all I am going to transmit to in the downlink, right? And the uplink, I say who all are going to transmit back to me. So within each you have a notion of a scheduled system. Okay. Okay. So let me just quickly summarize here. Okay. So the subscriber station may request bandwidths in 3 ways. One is using the contention request opportunities, which is the polling thing, or it can send a standalone message called a bandwidth request, or it can piggyback a bandwidth request message on a data packet. Okay, any of the 3 ways. This is fairly straightforward. There is no complexity involved here. Okay, base station may grant bandwidth in one of 2 modes. Okay, either it may grant bandwidth to an entire subscriber station. Okay, in the subscriber station there may be 10 different connections. Okay, no, just like think of it as n windows which you have opened on a machine. So you may be granted bandwidth for the entire machine, or you may be granted bandwidth for a per connection basis. Okay, mostly what is done is grant per connection. Okay, because grant per subscriber station gets a little bit more complex in order to maintain the QoS requirements. Okay, grants are notified through the UL map. Okay, so here is an example. Okay, you have a base station, you have a couple of subscriber stations. Okay, first thing, base station allocates bandwidth to the subscriber stations for transmitting the bandwidth request, right? SS1 transmits the bandwidth request, SS2 transmits the bandwidth request, and then base station allocates bandwidth to the subscribers for transmitting data based on their bandwidth request. Does that make sense? This is the basic bandwidth grant protocol. Okay, then they transmit their data and everything works out after that. Let me do this example. Okay, so let's say we have total uplink bytes that are available are 100 bytes. Okay, there are 2 subscriber stations and 1 base station. Okay, and the demands on the subscriber stations are like this. Subscriber 2 has UGS flow requirement of 10, RTPS 10, NRTPS 15, best effort 20, right? Now if all these numbers add up to 100, then what happens? There is no problem, right? Life is very comfortable. We can easily satisfy all the demands for both the subscribers. Okay, so unfortunately it doesn't add up to 100. So that's when we have the problem of figuring out how much allocation to give to each flow. Okay, so this is the key way in which to understand 802.16. Base station is going to compute it's going to compute the total demand per flow. Okay, so see the difference here. It is not the total demand per subscriber station. It's the total demand per flow that is being computed, because you want to give quality of service on a per flow basis. You say that okay, UGS I am going to give 30% of my bandwidth I am going to give to UGS, 20% to something else, and so on. Okay, so that is what it begins with. It says okay, so the proportion that we are using here is 4:3:2:1. Okay, so in the first round I give 40 bytes to the UGS flow, 30 bytes to the RTPS flow, 20 bytes to the NRTPS flow, and 10 bytes to the best effort flow. Okay, then what happens? You find that the UGS flow total demand is only 30, correct? Whereas you could allocate 40 to the UGS flow. Okay, so you have an excess supply here of 10 bytes. Okay, so that 10 bytes is all that you can, okay, that 10 bytes, and you have an excess supply of 8 bytes here. Okay, so you have 18 bytes extra which you have to now distribute among these two guys. So in the next round what you do is, you say excess bytes is 18, I am going to do a 2:1 proportion. So here I am going to give 12 extra bytes, and the best effort flow, for some reason it has gone there, I will give 6 extra bytes. Okay, so where does it come to? Now I have 32 bytes allocated for the NRTPS flow, right, and the total demand for NRTPS is 30, right. So I still have 2 bytes excess left over in this flow. So in the next round what I am going to do is, I am going to see that there are 2 bytes excess in this which are now allocated to the best effort flow. Okay, so the first thing that is done in a .16 network is allocation on the basis of flows. Okay, once I have done the allocation on the basis of flows, then you go back and see that which station should get how much. Okay, now it turns out that I have satisfied all the UGS flows, so both of these are satisfied. It turns out that I have satisfied the RTPS flows and the NRTPS flows, right. So the best effort flow, my total demand is 50, and the total allocation that is possible is 18, correct. So now what do? I can do it in many ways. I could either say that 9 of this will go to SS1, 9 of this will go to SS2, or I can again give this 18 in a 3:2 proportion depending upon the demand. Okay, so the standard does not specify how to do the best effort allocation. So this is just one example. Okay, so finally SS1 allocation can be 20 plus 12 plus 15 plus 9, SS2 allocation can be this. Okay, is that clear? So this is one of the key intricacies in .16. Okay, then now there are a lot of variants of this scheduling which you can take up with your students. All right. Okay, so this is a summary. WiMAX supports different applications with different types of QoS requirements, does adaptive scheduling. Initial deployments are underway, and it's a fertile area for studying the interplay of scheduling algorithms with Phi and Mac. Okay, so these are the references. Many of these slides and some other slides are also available on my web page. Okay, any questions?